So welcome everybody to the CAD Webinar Series. Today we have the seventh webinar with the title Deployment and Evaluation of Automated Truck Platooning. My name is Adrian Slocki. I'm with IKA, which is the Institute for Automotive Engineering of the Aachen University. And I'm pleased to have as a speaker my colleague Jens Kotte, who is an expert on truck automation, and he will present you this webinar today. Before we start, I have some basic information on the CAD initiative and on the webinar series. And on the next slide, you see the introduction to CAD. So CAD is an initiative together with Scout, consisting of around 30 partners and 40 associated partners, bringing you this webinar series. The project CAD aims at providing information to interested partners and the community on automated road transport. So that is the main reason, and one of the tools are the webinars, which present you interesting topics in the field of connected and automated driving. On the next slide, we see the activities of CAD. So there's an annual conference which is held once a year, which took place last year in Brussels. On the website, you find a digital knowledge base, you find strategic guidance, we develop position papers, we share knowledge on data sharing and data evaluation, and we have a great stakeholder network. We have thematic themes where we have kind of interest groups. Here on that slide, you see the different interest groups which we have formed. As you can see, those are mainly the relevant topics for automated driving, how to develop automated driving, how to evaluate and validate automated driving, and how to bring automated driving in the market in many different fields, ranging from connectivity to human factors, looking at infrastructures, business models, and so on and so on. So finally, please stay in touch with us. Hopefully you all know the CAD website. We have different means and different communication channels. One is clearly the website and the webinars. So you are in one currently. I understand you know how it works, but we also have a Twitter account where we post latest news. We have a newsletter. If you're not signed up to the newsletter, here's the URL to the newsletter. Quite some interesting news. And you can also have the possibility, if not done so already, to become an associated partner, and you can get all the information from the email address displayed here. Without further ado, I will now present the presenter. This is Jens Kotte. He's also from IKA, the Institute of Automotive Engineering. As I mentioned before, he's an expert on truck automation. He has many years experience in the field of ADAS and automated driving. He has been 1 year to the US, working in the Silicon Valley, founded there the FKA office, and he's now presenting you the webinar titled Development and Evaluation of Automated Trucks on the example of platooning. Before I give over the voice control to Jens, one more thing in terms of housekeeping. We will have at the end of his presentation a Q&A session, but it will for you not be a voice-based one, so not an audio one, but I would like you to ask to please send us the questions in the chat, and in the end we will go through the written questions of the chat and try to answer them as good as possible. And that's from my side. Thank you very much. Enjoy the webinar, and I hand over to Mr. Jens Kotte.
Okay, thank you for the nice introduction, Adrian, and welcome everybody to today's webinar. The topic is, as Adrian already told you, about development and evaluation of automated trucks on the example of platooning. And I was involved, for example, in the public-funded platooning projects Convoy and AZA, and also in some bilateral projects, and I always would like to give you some examples, some results from these projects to show you how you really can use this methodology in the whole process. So why do we talk about automation? Let's switch the slides. So what we have today and in the future, we have many challenges we have to face. This is, for example, the climate change. We have to find solutions to make the traffic more efficient, more energy efficient, but also traffic efficiency is quite important. In the future, we have the problems with the urbanization, many accidents, limited resources. And for all of this, we need solutions to really have a good future with mobility for everyone. And what we think, and many people think, is that automation can be part of a solution and can be quite helpful in this topic. If we talk about automation, all of you probably know the levels of automation. We have talked about it quite often in the last year, so that I don't want to go into the level definition into detail today. But I also would like to introduce kind of levels of connectivity, because this is quite important if we talk about platooning, to really show you the differences between an ACC system and an cooperative ACC system. And that's where we start, for example, with normal systems that we have in today's cars, for example, and adaptive cruise control, or maybe also already in a traffic jam assist. We have no kind of connectivity. In some systems, we can use state-of-the-art connectivity. This is, for example, radio-based danger warnings, and we can improve these systems. So we can have a better route choice, or we can avoid traffic jams, for example. This can be done with state-of-the-art connectivity already. But if we talk about platooning and other safety relevant cases, we need a robust and secure connectivity. And this is what we need for platooning and cooperative ACC systems, for example. And this shows quite good how connectivity can make a regular system better. For example, with an ACC system based on radar, we have to have distances or gaps between the cars higher than 20 meters. If we use cooperative ACC, so we use the connectivity, a robust and secure connectivity between the cars, we can use shorter gaps. And with shorter gaps, we are more energy efficient, but also can increase the traffic efficiency. And this slide also helps to really distinguish between different platooning systems, because if we talk about platooning, it's sometimes completely different systems we are talking about. For the first one, what is in many minds today is the cooperative ACC system. It's often called platooning, but in my definition today, when I talk today about cooperative ACC systems, I will talk about a level 1 system with communication, so that we just take over the longitudinal control, and if the driver still has to steer, from my perspective, the gaps has to be larger than 50 meters so that he can still control the car or the truck safely. There are other definitions, for example, one from Stephen Schlederer from PATH. They say cooperative ACC systems use a constant time gap, and platooning systems use a constant distance gap. But today I will focus on cooperative ACC system as a level 1 system, and if I talk about platooning, I will talk about level 3 or level 4 systems. And here, what we can see, if we talk platooning, the longitudinal and lateral control is taken over by the system. So the driver does not have to steer. The driver can relax, and the second or the following cars just follow the first truck. And if we have the steering control by the car, we also have not an issue that we can use these shorter gaps, because the driver is not responsible anymore for the steering. And this is important, and this makes it much more difficult. If we have to control the steering system, and we just have a gap of 10 meters, it is quite difficult to really measure the lane markings, so that the control is not really easy, but it's feasible. We have shown in many projects. If we distinguish between level 3 and level 4 platooning, the one is that we have the driver still in the loop a little bit, so that he can take over control in certain situations, for example, construction zones, where we can warn him in advance, maybe 1 minute in advance. And in level 4 system, I expect that the platooning system will also work in construction zones, for example. Platooning is not a topic that was started in the last years. So I guess the number of projects that work on platooning increased in the last years, but it started, as we can see here on this slide, quite early. For example, with the Promote Chauffeur project in Europe from 2000 to 2003. First platoon system was developed and researched in this kind of project. This project was followed by the German funded project Convoy. Then there was Sartre, Compagnon, and there will be, and starting mid of this year, a new project quite interesting called Ensemble, where all the European truck OEMs work together on a multi-brand platoon system. This slide just should show that it's not a new topic. It has a long history, and we will see later on the results that it's good that we have this history, because we are on a good level today. If we talk about automation and connectivity, we have to face different challenges. For example, the weather conditions can change, and we have to prepare the systems. Either the systems has to be developed that they can handle these situations, or they have to detect these situations and give the control back to the driver, so that we always have a secure system. Another challenge is the driver. And this is a topic which is even more difficult if we talk about truck automation, because the cabin is much larger. The driver can do everything if the car is doing or is driving automatically. So we need to observe the driver. This is, from the one hand side, important if the driver has to take over control again, but also important if we talk about passive safety, because the airbag, for example, will not work in this situation. Third example for challenge is the societal expectation, which is quite important. If we trust the media and all the reports, if we talk about automation, we expect that we will have vision 0, and we will have it in mixed traffic immediately. So there will be some accidents, and there will be especially also some accidents caused by automated vehicles, because people also don't expect what they are doing. An automated vehicle will always follow the rules, and normal drivers don't do. And this is something people don't consider in traffic when they see an automated vehicle the first time. Let's go to the truck-specific challenges. If we talk about automation, we have here a nice picture from Mercedes-Benz, where we can see the variations of dimensions. And this is quite important. If we talk about truck automation, and we always use, for example, a camera as a sensor, it is a quite big difference if the sensor or the camera is mounted on a height of 1 meter, or maybe on the left side in the big truck on a height of 2 meters. The algorithms have to be adapted to this position to really work in a good way. So we have to consider this if we talk about truck platooning and truck automation. We also have a challenge which is specific to trucks, is the configuration variation. If we talk, the system has to know, for example, if the truck is alone or if it is a tractor-trailer combination, because the weight of the system can be completely different from 12 tons to 40 tons in Europe. And this has to be considered, and the function has to know it to really have good controllers and good systems. And another example for a truck-specific challenge, a quite important one, are large pitch angles. What we see, for example, if we don't have the trailer on the truck and we accelerate or brake, we have really large pitch angles, and this figures should show what the sensors can see in this situation, and that can be quite difficult. And if we talk about gaps of 10 meters, for example, in a platoon, we really have to consider this, that we have maybe some situations where we lose the lane markings. To model these challenges and also to identify actions that are necessary, we try to identify a 5-level model, which is shown on this slide, where we have a technical level, where we have an interaction level, an economic level, a legal level, and a social level. And if we go, for example, for a necessary action, if we talk about automation and have a look on the interaction level, we have to define for level 3 systems, for example, safe transitions from the system control to the control of the driver. This has to be studied, and we have to find solutions for that. If we go to the legal level, we need, of course, rules on driver behavior. What is the driver allowed to do if he is driving an automated truck, for example? The acceptance of societal groups, also quite important. If people don't accept automated trucks or automated cars because they are afraid that they steal jobs or something like this, that can be a really difficult discussion and can destroy the whole story. And we really have to prepare the groups around and show them the benefits. So we also have to work on this level. We as engineers, we like, of course, mostly to work on the technical level. And here, of course, we have also many homeworks to do. For example, the driver monitoring to detect the drivers. Where are they in the cabin? What are they allowed to do? Maybe to adapt the passive safety systems to make a safe system in the end. We have to develop nice and safe HMI concepts and environmental perceptions and the understanding and many more things. This model should help us to really identify different steps we have to do in the future and today. For the development and to solve these, especially the technical problems or issues, I will now introduce an holistic methodology approach and a modular connected infrastructure, which is shown on this slide, where we have first on the left side the idea. So we think about a new platooning system. Then we have to, of course, define the concept. We have to evaluate the concept, and we have to specify the function and the function environment. And this is quite important. For example, if we talk about platooning, we have to solve the question in the beginning. Is it good to have a gap of 5 meters? Is it good to have a gap of 10 meters? Is it good to have a gap of 20 meters? What is the should we include lateral control? Should we just use longitudinal control? These are quite important steps we can identify quite early in this development concept, and I show you later how we can do it. After the specification, of course, we have to develop software, have to develop components and the hardware in the loop, and have to validate everything. So first, of course, hardware in the loop test, then we have to go in on the function validation, and then in the end, quite important, and that's a good step where we today with platooning, field operational tests. How can we support all these questions that we have to answer in the development and evaluation process? One quite important tool is a multi-scale traffic simulation. I will show you later how that looks like, and I will also show you some results from platooning projects where a kind of multi-scale traffic simulation was used to identify specific parameters of the platoon. A second really important tool is a driving simulator. Always, if we have to include the driver, and we have to include him quite early in the process to really identify also issues related to the driver, we can use a kind of time machine, and this is a driving simulator. For example, if we would like to identify what gaps are accepted by a driver so that he still feels safe, this can be done in an early phase in a driving simulator, and that was done, for example, in Convoy. If we have the software and the hardware in the loop, we have to bring all this on a research platform. This can be a platform like this one, the Speedy, a nice concept car, but mainly it will be normal trucks, today's trucks that are equipped with special sensors so that we can validate and really do the function tests. And where can we do the function tests? On intelligent proving grounds. In the past, it was okay if we just go on a proving ground that has enough space to really make safe maneuvers. But if we talk about, for example, also communication to the infrastructure and the communication between the cars, we have to also include these technologies inside these intelligent proving grounds to test the systems in a quite normal environment. If we have done all these tests on a proving ground, we can go on field operational tests and analyze what is the traffic around doing and what are the impacts on traffic, and what do we have to include in the function to make the system much better. Let's start with a multi-scale traffic simulation. As one part, this is a quite complex graphic, but it shows a little bit the different layers of the multi-scale traffic simulation. We have on the bottom, we have the components, then we have a system level, we have a vehicle level, and then we have a traffic level. And if we talk about a platooning system, for example, it can be just interested to see what is a good gap. So we go on a vehicle level and see what is the difference on the traffic efficiency if we use a gap of 10 meters or if we use a gap of 20 meters. But if we also would like to analyze, and that makes it much more complex, of course, what is the best sensor suit to really have these or to make sure that the gaps we have chosen are safe, we have to also include sensor models. So we can do the same test with sensor setup A, B, or C and see what are the impacts on traffic, for example. If we have a look now in the results from Sartre, for example, there were also we have done in the project simulations on the air velocity to identify, okay, what gaps are good to have an good energy efficiency for all the trucks, and here also on Sartre cars, also passenger cars, what are good gaps and which are gaps which are not so good because the effects are not really stable. And what we can see here, for example, if we go to the lowest picture, we have here a gap of 50 meters. And what we can see here is if we have a gap of 50 meters, the second truck is not anymore in the wake turbulence behind the first truck, so that the first truck will not save any fuel anymore if the truck distance is larger than 50 meters. This is of course a simulation results. We also have done test results on a test track I show later, but this is a quite good indeed in the beginning to really say, okay, to really have a good efficiency for the overall system, we should use maybe gaps shorter than 50 meters. We can also simulate, for example, the frontal pressure. That was also done in Sartre, and here you can see for one example gap how the pressure difference is between the first and the second truck. I told you also that it's quite important to identify, especially if we talk about platooning, what is the impact on the traffic flow. And for that, we did also in Sartre simulations on traffic efficiency. And here is the example of the of some results where we went on a highway for the simulation, and we have a reduction from 3 lanes to 2 lanes after a highway entrance. And what we can see here, we have these 3 pictures. On the left side, there is no platoon. So this is just all the cars or all the trucks that are driving alone, no platooning. In the middle, the picture shows the results of 2 platoons with each 5 vehicles. So we took from all the cars that are driving around this area, we have chosen 10 vehicles and put them in 2 platoons. And as we can see here, the red area is getting smaller, which shows that the average speed gets higher in this situation. And if we not only choose 5 vehicles per platoon, we choose 10 vehicles on the right side. And here we can see we almost just have no wet area anymore. So it's even a better effect, of course. So that shows, of course, we need to bring as much as possible vehicles in one platoon. But we also, and that is shown in this slide, we also have to consider the effect on the entry ramp. And this is quite important because if, of course, if we put a lot of trucks inside with small gaps in one platoon, people on the entry ramp will get an issue to enter the highway. And this is shown on this slide with the simulation here. On the left side, again, no platoon. And here you can see the speeds on the highway ramp. So here it looks quite good with no platoon. And if we have a look on the right side with a platoon with 10 trucks, it's getting quite difficult for people to enter the highway. And the simulation shows that many cars have to stop here. And this is really a big issue. So we really have to find the best solution to, of course, increase the efficiency on the highway and still have a good efficiency on the entry ramp. And for this, it really helps to have the simulations to identify, okay, we need or we can have platoons with at most 4 trucks and a 10-meter gap. This was one result from Convoy, for example. Another simulation was done in the US. It's quite new, so it's from the last year. Also quite important result. This was done on a 24-kilometer corridor, which is quite crowded, and it's between the port of Long Beach and downtown Los Angeles. And what we can see if we bring in a cooperative ACC system with a 1.2 seconds time gap, the aerodynamic drag reduction was only 0.5%. This is not a lot, but the energy saving from traffic smoothing was 2.5%. So it's still a really good benefit, and we could also increase the average truck speed from 53 to 64 kph. So this helps again to identify where a platoon can be used and what is a good configuration of the platoon. Now, if we have identified the system parameters, the configurations in first simulations, we have to test the driver view on this configuration. For example, what gap is accepted. And for that, different tools are possible and different simulators can be used. And we have, for example, on the left-hand side, a quite simple simulator, static simulators, which are quite cheap. In the middle, we have a dynamic driving simulator, and on the right side, we have a high-fidelity driving simulator. So what we would like to show here is that you need for different research questions different kinds of simulators. In Convoy, in the public-funded project Convoy, the simulators were used to identify the acceptance of truck drivers inside a truck platoon quite early in the development process. And it was quite nice to ask people before the project and after they experience the functions, the platooning functions. And this was quite nice to see. Before people have experienced a platoon, 20% just responded positively. But after they have tested the system in the driving simulator, after they experience it, 54% responds positively, and I think that even more will think positive about it if they have experienced it on a test track or in reality. We also investigate, and this is quite important if we talk about gaps of 10 meters, the workload of the drivers. If it differs from a normal driving situation, and what we could see in Convoy, for example, with the 10-meter gaps, there was no significant difference between the Convoy, the platooning driving, and the normal drive. Research platforms, what we have in many projects and what is quite useful, of course, are normal trucks that we equip with special sensors to identify or to research the functions and to develop first prototypes. Here is just one example, our test truck, which is used in many projects, and what we see in many projects today already, and also on the European Truck Platooning Challenge. These are state-of-the-art trucks with a little bit more sensors equipped, but which can be also quite important to bring these kind of functions already in new concept cars. What we see, for example, and I'll show you later some results, are if we combine a platoon with energy efficient trailers, that we have even a better result. And so that makes sense sometimes to also include these new functions in concept cars. Intelligent proving grounds, also really important part. If we have to include, for example, the communication with the infrastructure. If we would like to hand over, for example, the platooning control from automated control to manual control in front of a conjunction zone, we have to test it in a safe environment, and for that, of course, we need these communication infrastructure. And there are many test tracks worldwide today, for example, M-City, but also Aldenhoven Testing Center with CERN, where you can test these systems in a really safe environment, where you can also where you can test communication errors and stuff like this. And this is quite important if we talk about systems that rely on communication, that we also include these tests inside the development and evaluation phase. What did we do in Convoy, and what every system did, Sartre and Compagnon, before they went on a road, of course, they did tests on a proving ground to make sure that the operation in real traffic is safe, where you do some cut-in maneuvers and other maneuvers to really make sure, okay, we believe that the system will be safe before we go in real traffic. But proving grounds can also help to really study the benefits from a platoon, and this is a slide which is showing the results from the Sartre project, where the tests were done in Idiada, the test ground in Barcelona, and where we tested under perfect conditions what are the benefits regarding fuel saving in a platoon. And what we can see here, for example, we have a mixed platoon in Sartre, so we have 2 trucks and 3 passenger cars. And if we just focus on the trucks, we can see the following truck can have a fuel saving potential of 16% with a gap of 5 meters. And if we talk about 5 meters, also the first truck. So the leading truck has still a benefit of around 7% fuel savings. And if we go back, and this is what we have seen also in the simulation, of course, was if we talk about 50-meter gaps, this is on the right side of this graph, the benefit for the leading truck is almost 0. Here it's still 1, but if we go to 60 meters, for example, there will be no further benefit. And this shows that the simulations were not so wrong in the beginning to say, okay, the benefit for the leading truck is limited to a specific distance, with a specific gap. And of course, it's also for the following truck, but it's different. So with a gap of 50 meters, the following truck can still have a fuel saving potential of 8%. If we talk about other trucks, so if we talk about US trucks, these are some results from proving ground tests which were done in Canada, I guess, in the last year. And they show quite similar results. And on this test, I like that they have combined the platooning system with aerodynamic trailers. And what they could see is that they even have a greater percentage fuel saving for platooning for the aerodynamic trailer compared to standard trailer configuration. This was 0.5% to 2% higher, depending on the separating distance. The net fuel savings for the fuel vehicle platoon was between 5.2% and 7.8%, but here we talk about gaps of 17 meters, so it's a little bit different to the tests in Barcelona from CAD. After we have shown on a test track that the system is safe, we of course have to go into the field, do field operational tests to really experience what can happen if we combine it with mixed traffic. What does mixed traffic think about it? And for that, of course, we have to go into the field. And here's just one video. I hope it will work. It's in German, but this shows the test runs in 2009. This was quite early in 2009. As you can see here, we have gaps of 10 meters. We run in mixed traffic, but we have safety cars around. And this test really helped us to understand how the environmental traffic will react on a platoon. And here are some results I will present today. What we could analyze was based on the videos you can see here on the bottom is that we had over 2,400 overtaking maneuvers while we were driving on the highways. and which is quite important. The general result was that we haven't had significant influence on the surrounding traffic. People just drove around as they drove always. They of course looked a little bit because of the police car in the back, but we haven't experienced any significant influence on the surrounding traffic. But what we experienced were cutting maneuvers, and we expected, for example, with a 10-meter gap, that we won't see any or a lot cutting maneuvers. And overall, I'm not sure, it was around 3,000 kilometers we have driven in a platoon. We experienced with a gap of 10 to 50 meters, six cut-in maneuvers. And this was always in front of an entry or exit ramp. And this was because other truck drivers expect always a friendly behavior of a convoy, so of another truck driver. So, and the convoy system was not designed in this manner. So it was just the signs on the platoon that showed, okay, here is the platoon driving, but people didn't know what that mean, and the convoy didn't increase the gap automatically to let people cut in. If the people cut it in, it wasn't an issue for the system. So the system was still safe. It always worked quite good. So increased then the gap. But of course, this gap increasement is quite inefficient. So if we always have to brake or accelerate in front or behind an entry-exit ramps, we will lose a lot of energy efficiency. So that's what we have to consider in future platoon configuration. Maybe it's better to just have 2 trucks in a platoon. Maybe it's better to have shorter gaps. This is part of future evaluations, and that's why it's quite important to have more and more field operational tests for platoons. And as we can see here on the slide, there are many field operational tests going on in the future, and some were already done in the past. So if we have seen, for example, Sartre, we talked a lot about this project. They did some tests on Spanish roads. Companion did some real-world tests or field operational tests. Then we had, as a big and great event, the European Truck Platooning Challenge in 2016, where all the truck OEMs were involved and experienced platooning around Europe. And what we see now, and this is quite nice on the slide, what we see is that now we have in 2018 ongoing even more projects that do field operational tests on the topic of platooning. And we have this ensemble project, we talked about it. We have in Germany the DB Schenker and MAN activities on the A9. We have in the UK the platooning trials, and we have Sweden for platooning, for example. But also in the US, of course, they are still working on this topic and do field operational tests. And this is also quite important because the traffic in the US is not always comparable to the traffic in Europe. So the results can be quite differently. And here's just one example of a project from Caltrains, where they think about a dedicated truck lane in Los Angeles in 2020 to connect a corridor from the ports to downtown LA. And they just would like to allow platoons on these lanes, and they did already, to show the effects a little bit, demos in Northern California and Southern California, and Turner Fairbanks in 2016 and 2017. Also in Singapore, there's a new field operational test started in 2017 with Toyota and Scania. It's a 3-year project. The first year is to design and refine the truck platoons they have developed already. in Sweden and Japan. And in the second part of the project, there will be a 2-year trial, also a 10-kilometer long test route along West Coast Highway. And we are quite excited to see the results of these tests. If we try to use all these parts together, we should also identify relevant situations. So if we go, for example, in a traffic simulation, we need to know what are relevant situations the system has to work in. What are situations which could be critical or relevant for the systems? For example, for platoon, it is entry and exit ramps. We also need it for the driving simulator. We need to know where is the driver, a quite important part of the overall concept, so that we have to test the driver just in these special situations, because we can't test everything on a test track anymore. This is too much. So if we have it, we also have to go to hardware in the loop test, and of course, again, we need exactly to know which situations, which scenarios have to be tested hardware in the loop. And to really get this database of relevant situations, we have to results from the further tests. So for example, from the driving simulator test, we can generate new scenarios to determine how critical or relevant a situation is for the driver. From the field operational test, we gather new information, gather new situations that has to be tested on the left side, for example, in the simulation. This is, for example, if we go back to platooning, the issue with the entry and exit ramps. We saw in the beginning, we thought, okay, a platoon with 4 trucks and 10-meter gaps will be quite okay. But then we saw, okay, we still have cut-in maneuvers. Maybe we can decrease this number, so we can go back to the simulation and simulate again specific entry-exit ramps with a platoon to identify the best configuration of a platoon. And this should be a living database so that we always get new information, new scenarios, to get new test data for all the different steps of this methodology approach. And this is also the end of my presentation. And now we are open for some questions. So I've seen there's the first question about the 50 meters. The 50 meters, there is now research done why it is exactly 50 meters. This is just an over-the-thumb value. So from the experience I've done in the test, so I've driven, I would say, over 10,000 kilometers in a platoon. And if you have 10-meter gap, you won't see anything around in front of the first truck, for example. If you have a 50-meter gap, you feel much safer as a driver in the following truck. And this is not good. Also, a kind of distance we experience a lot on highways today, but it's not really a study done that says, okay, 50 meter is the gap we should use. It's just an over-the-thumb estimation. So I see there is another question about the AZA level. This is a quite difficult question, because of course it depends on the exact system we talk about. If we talk about a level 1 system or about a level 3, level 4 system. What was done in Convoy, it was not ASIL because it was earlier. I guess it was, I have to look into it, SIL2. So another question is the what was the solution for the ego motion and localization? Was it DGPS or using vehicle initial sensors? It was a vehicle initial sensor. So we haven't used any DGPS systems in Convoy or Sartre. Sorry. Another question is, could you foresee a business model that rewards the platooning lead truck in some way, as clearly the following truck get more benefit? Yes, I think there are some quite interesting business models. On the one hand side, of course, you can have platoons just from one company. It's not really interesting, but it's possible for the beginning. And then if you have really nice service of a platooning, you can buy time, for example, and you can have a transfer of money from the second truck to the first truck, for example. But of course, you need for that an organization that is handling all the service. And one startup that is working on this is, for example, Peloton in the US. They are developing a service that is also considering this topic about how does the first truck also benefit from it. Then there's a question about connectivity. Do you consider ITS G5? Yes. So this is also a really good question, because G5 will be used in, I guess, many platooning projects, and is really important for that. Maybe in the future we also have to consider 5G as a redundant sensor, but research has to show if it's necessary or if it is enough if we have just different channels on the G5 network. The cut-in maneuvers were between the trucks. So I was driving most of the time one of the last trucks, and I had some cut-in maneuvers then, for example, between the third and the fourth truck. And so it was not critical for us, so it was really fine. But it is really just the energy efficiency we have to consider. If we have these cut-in maneuvers, they are really bad for energy efficiency. For safety, it's completely fine, because the systems can really handle these situations. We had to prove it in advance, so that is not an issue. But that was mainly between the third and the fourth truck, and sometimes between the second and the third truck. There's a question about the a country, a government that is currently advanced in terms of regulation and test implementation of platooning systems. This is also hard to answer. So as we can see here, that many countries would like to really support this topic. This can be done in the Netherlands, for example. They have organized this platooning challenge and also this Declaration of Amsterdam. But we can see also in Germany, for example, that they support this topic by the A9 test bed, where we have the MAN activities, for example. But also in Sweden, it's quite good because of the projects that are currently running there. So I guess many of the governments really try to support these topics, but I can't say that some of them is more advanced than the other one. There's a question about cooperative ACC algorithms, how they work. Are they based on predictive controls? Of course, I can't say or talk about all the systems because I've just seen our systems, but predictive control is, of course, a quite important part. Then there's a question, do you observe any or many stop at the on-ramp acceleration lane to wait for platoons? I haven't seen anything implemented yet, but I've observed some discussions that it could be possible to place some traffic lights there to make it this way. Have to look, or maybe it's also still the Sartre documentation is still online. There you can find a deliverable where the tests are described and also the results, but the results were good, so I don't see any issues in this topic. Then there is the question about the influence of environmental conditions like Sidewind. I don't have any results here. That was quite good in Barcelona. So we haven't had any sidewinds for the results. This was quite important to identify these numbers I've shown on a stable condition, but of course it would be also quite interesting in the future to identify numbers under special environmental conditions. But so far I don't know any study that has really looked into that quite deeply. Okay, so I guess there are no further questions. Thank you very much to be part of this webinar. If you have any further questions, just contact me. You can see here my contact information, but I guess they will also be online. So you're always invited to write me an email or call me, and we can discuss these topics a little bit more deeply. Thank you.